Welcome to this fascinating journey into the world of chordate biology. Today, we are going to explore locomotory appendages. We will uncover how nature uses a single, elegant skeletal blueprint to allow animals to run across savannas, swim in deep oceans, and fly through the sky. Let us dive in and see how biology meets mechanical engineering. To begin, imagine you are given a basic set of Lego blocks. You could build a fast race car, a heavy bulldozer, or even an airplane, all using the exact same pieces. In the animal kingdom, nature does something very similar. Before we look at the complex biology, it is important to understand this simple idea. The arms, legs, wings, and flippers of animals are what we call locomotory appendages. Whether a bat is flying, a whale is swimming, or a cheetah is sprinting, they are all using modified versions of the exact same basic bones. Now that we understand the basic concept, let us look at the formal biological structure. In the study of chordates, locomotory appendages refer to the paired outgrowths of the body that are primarily adapted for movement. This includes pectoral and pelvic fins in fishes, or forelimbs and hind limbs in land animals. The underlying structural blueprint for terrestrial chordates is known as the pentadactyl limb. This standard pattern consists of one upper bone, two lower bones, wrist bones, and 5 digits. This specific arrangement is the foundational architecture from which all terrestrial animal limbs are built. Building on this pentadactyl blueprint, we must ask how animals look so different today. Through a magnificent process called adaptive radiation, this single ancestral limb structure has been evolutionarily modified into vastly different forms to suit specific environmental niches. For example, the bones may become elongated for running, shortened and robust for digging, or webbed and flattened for swimming. Despite their drastically different outward appearances and functions, these appendages share a homologous skeletal architecture. This means they all evolved from the exact same common ancestor, perfectly adapting to survive in their unique habitats. Understanding these structures is not just about biology. It has massive real-world applications. Movement dictates almost every aspect of an animal's survival. Without the ability to move efficiently, an animal can't escape predators, hunt for food, or migrate. In the modern world, human engineers study these biological appendages to design better robots and prosthetics in a field called biomimetics. For instance, the flexible fins of fish have inspired highly maneuverable underwater drones, while the energy-storing tendons in a kangaroo's leg have influenced the design of running blades for Paralympic athletes. Nature is our greatest engineer. To truly understand how these appendages work, we must transition from biology to the physics of animal movement. Biologists use specific formulas to measure how efficiently an animal travels. This brings us to the basic equation for stride velocity. The formula is v equals f times lambda. Here, the variable v represents the velocity, or speed of the animal, measured in meters per second. The symbol f stands for the stride frequency, which is the number of steps the animal takes per second. Finally, the Greek letter lambda represents the stride length, which is the distance covered in a single step, measured in meters. If an animal wants to run faster, it must physically increase its stride length by evolving longer legs, or increase its stride frequency by moving its legs much quicker. Now that we have our formula, let us see this with a concrete example. Imagine a cheetah hunting on the open savanna. We are given that its highly specialized long limbs allow it to cover a massive distance of 7 meters in a single stride. During a high-speed sprint, it takes 4 strides every single second. We need to calculate the overall velocity. We substitute our given values into the equation, multiplying the frequency of 4 by the length of 7. This step combines the two independent variables of the animal's gait. The multiplication yields our final calculated answer of 28 meters per second. This physically means the cheetah covers 28 meters of ground every single second, demonstrating exactly why a long stride length is so beneficial for hunting. Having seen how stride length affects speed, we can look at another powerful way to analyze locomotory appendages. We can view them through the physics of lever mechanics. Animal limbs act exactly like mechanical levers. In this system, the joints act as pivot points, and the muscles provide the input force. Depending on exactly where the muscle attaches to the bone, the limb can either be optimized for high speed or high force. This is a crucial evolutionary trade-off. An animal cannot have both maximum force and maximum speed in the same limb, so nature must choose based on the animal's survival needs. This concept of lever optimization leads us directly to the mathematical formula for mechanical advantage. The formula is MA equals L in divided by L out. MA stands for mechanical advantage, which is a unitless number that tells us how much a limb multiplies the force produced by the muscles. The symbol L in represents the in-lever length, which is the physical distance from the joint pivot to where the muscle attaches to the bone. The symbol L out represents the out-lever length, which is the distance from the joint pivot to the end of the limb, like the foot or claw. If an animal has a long muscle attachment and a short limb, it will have a high mechanical advantage, producing massive force. Conversely, a large out lever decreases force, but allows the limb to move much faster. Before we compare different animals, let us calculate the mechanical advantage for a specialized digger. An armadillo has a specialized digging forelimb. We are given that the muscle attaches 4 centimeters from the elbow joint, making our in-lever 4. The total limb length is 12 centimeters, making our out-lever 12. We need to calculate the mechanical advantage to understand its force output. We divide the in-lever of 4 by the out-lever of 12. This gives a mechanical advantage of approximately 0.333. Because the out lever is relatively short, the muscle force is not diluted over a long distance. This physically means the armadillo generates a very high mechanical force, perfectly suited for digging through tough soil. Now let us perform the exact same calculation for a running animal to see the contrast. A horse has a running limb where the muscle also attaches 4 centimeters from the joint, so the in-lever is 4. However, the limb is 40 centimeters long, making the out-lever 40. We divide the in-lever of 4 by the out-lever of 40. This calculation gives a mechanical advantage of exactly 0.10. This much lower number indicates that the horse's limb is not designed for maximizing force. Instead, the extremely long out lever means that a small contraction of the muscle results in a massive sweeping movement at the hoof, enabling high-speed running. So we have calculated the values for both animals. This brings us to proving the mathematical trade-off between force and speed in biological systems. We start by setting up a direct comparison between the two mechanical advantages we just found. We take the armadillo's mechanical advantage of 0.333 and divide it by the horse's mechanical advantage of 0.10. By setting up this ratio, we are mathematically evaluating exactly how much more force the fossorial, or digging, limb produces compared to the cursorial, or running, limb. This step is crucial to see the true scale of evolutionary adaptation. Continuing our derivation, we calculate the final ratio. Dividing 0.333 by 0.10 yields 3.33. This mathematically proves that the armadillo's limb is over 3 times better at multiplying force than the horse's limb. The intuition here is beautiful. The armadillo is perfectly adapted for powerful digging, while the horse sacrifices this force to have a much longer outlever. This longer outlever allows the tip of its hoof to swing incredibly fast. We have successfully proven the biological principle that adaptive radiation tweaks the exact same basic bones to achieve completely different, mutually exclusive mechanical goals. Let us visualize everything we have just proven by looking at this diagram. On the left, you see the fossorial, or digging, limb of the armadillo. Notice the short, robust bones. The distance labeled L in is the in lever, and L out is the out lever. Because L out is short, the output force arrow at the claws is very large. Now look at the right side, showing the cursorial, or running, limb of the horse. The L in distance is similar, but the L out distance stretching down to the hoof is massive. Consequently, the output force arrow is much smaller, but this long lever allows the hoof to cover a huge distance rapidly. This diagram perfectly captures the biomechanical trade-off. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that all terrestrial chordate limbs evolved from a single shared pentadactyl blueprint. Second, through adaptive radiation, nature modifies these bone lengths to perfectly match an animal's survival needs. Third, we saw that an animal's speed is a direct product of its stride length and frequency. Finally, we proved that mechanical advantage dictates a strict trade-off. Limbs can be optimized for powerful force, like digging, or high speed, like running, but never both. You now have a solid understanding of the biomechanics of locomotory appendages.